All right, number
10 or 11 and or 11.
Ooh, yeah.
okay. So number 12, the equation of the line tangent to the curve. So this is the curve right here. All right, and this is the tangent line. Now again, keep in mind, tangent line, any line, the equation is, this right here. We've written it various ways, but and the key is the slope. The slope of the tangent line is the derivative. The slope of the tangent line is the derivative. And so they tell you at -2, and right here you can see that the slope would be 1, right? The slope of this line is 1. So that tells you this derivative has to be 1. That's what you got to do. So this derivative has to equal 1. And then, so you just do that derivative. So what's that? Because because this is the tangent line, it has a slope of 1. And that's the same slope as the derivative, because that's what slope of the tangent line is the derivative. So we do a quotient rule. So derivative of the top, which would be k, right? K is just a number in front of the x, times the bottom left alone, k plus x, minus the top left alone, kx plus 8, times the derivative of the bottom, which is derivative of k is 0, derivative of x is 1, all over the bottom squared. So you distribute this, that'd be k squared. Well, actually, what could we do right now before I get too carried away? There's another piece of information. It's got to equal 1, and then what else? When x equals -2. So I can put a -2 in there. So I can put a -2 right in there, and I can put a -2 right in there, and I can put a -2 right in there. So when I take k times k, I get k squared. K times -2 is -2k minus, and then here I would have -2k, and then minus 8, because I got to distribute that. Oh, whoops, I guess I have parentheses here. So I don't have to distribute that yet because I put parentheses. So that'd be -2k plus 8, and then down here I've got k minus 2 all squared. And that's got to equal 1. And this is a no calculator. So this would be k squared minus 2k plus 2k. So those are going to cancel out. So I got k squared minus 8 over k minus 2 all squared equals 1. And so I could multiply that over to that side. So I got k squared minus 8 equals k minus 2 squared. Probably a good idea to FOIL that out at this point, because it doesn't look like anything else is going to happen nice. But that's good because the k squareds are going to drop out. And so I'm going to get -4k plus 4. Now I can subtract 4, which is going to be -12. Divide by -4, I'm going to get 3. But again, the calculus part of that, a lot of algebra, the calculus part of that is understand what's it saying. The equation of the tangent line, or the slope of the tangent line, is the slope of the curve, is the derivative. That's what derivative is by definition. The derivative is the slope of the tangent line. So the derivative's got to equal to 1. You plug a -2 in there, you find it. All right, what else? 10, 11? Both? So 10?
Sure.
Well, I mean, we can talk about both of them real quick, but isn't this, did we mention this on Thursday? I thought somebody asked about this one. Yeah, where you just do, you just turn tangent into this. And then you let u equal cosine. So the du would be negative sine. And so you'd end up with a 2. You sub all those things out. The 2 would be there, it'd be negative. You have 1 over u. So that's -2 ln u, and the ln is cosine. And then, of course, they said from 0 to pi halves. Why is that important? I mean, if I look at these, so I got -2 ln cosine. Now, I look, and none of those are choices. And none of them have absolute value. Now, partly you might have just got lucky and you'd have forgot the absolute value and you wouldn't even have thought about it, so okay. But if you'd have been do it right, you'd have had absolute value, and it might have been confusing. You just said, why is there no absolute value? And it would have really been confusing if E would have been none of the above. They don't do that to you very often, fortunately. Okay? Because if you got that answer and this was none of the above, you might have went with that. Well, what do you do with this negative? What can you do on a log with something out in front? You can put it on the inside as a power, right? Remember we talked about that? LN4, they always try to get you with these kind of things. On the first 28 questions in any packet, the no calculator multiple choice, they're going to get you on logs and trig and algebra. That's where it's at. That's where that stuff is all going to be. And so you're going to see a lot of natural logs. You're going to see a lot of trig stuff. Okay? And there's some of it, there's both of it in this problem. The trig is right here, 0 to pi halves. That's quadrant 1, right? What's cosine in quadrant 1? Positive. Cosine is positive in quadrant 1. So you see why there's no absolute value bars on any of the answers? So when you're from 0 to pi halves, cosine is positive, so there's no need for the absolute value because cosine is positive. Okay? That's why 0 to pi halves is there. ln4, remember we've talked about, that's the same as 2 ln2, or excuse me, that's the same as ln of 2 squared. And you bring the 2 down in front, and that's 2 ln2. Well, you can do the reverse. You can bring that 2 in as a power. Well, that's what we can do here. So I can bring this in as a power. All right? And so what do you get? You get ln of cosine x to the negative 2 power. Well, what's cosine x to the negative 2 power? Flip it. That's secant squared. That's 1 over cosine squared, which is secant squared. So this is ln of secant squared, which is C. All right? Now, another thing they could have done is not put the negative 2 in. They could have just put a negative 1 in as a power, left the 2 out there. If they put the negative 1 in, now you got cosine negative 1. What's that? Secant. So 2 ln secant would have been an answer. Now it's not up here. They got secant, ln secant of 2x. You know, they left the 2 out here, but then it's a cosine. I mean, so there's a lot of different ways they could have written that, just kind of testing you on your knowledge of these different log properties and the trig kind of stuff. So a lot of that all in one problem. And, of course, there's a lot of calculus there, too, knowing to do that and to do a U substitution. So, okay, good problem. A good problem if you think a good problem is something that makes you think about a lot of stuff. You might not think that's a bad problem. But anyway, this one we thought was okay. I mean, here it's nice. It gave us the U substitution. I think the key is you had to change the 0 and the 2. Right? That's the thing you had to make sure you did. So if you let u equal x squared plus 1, the du is the 2x dx. This one isn't just simple, though, is it? I mean, yeah, the x cubed is x times x squared. I think that's the key to that one. You got to, like the 2, I can move that over here. So I have a 1/2 du. So that's x dx. So now in my substitution, my x dx would take that out of there. Yeah, so in the bottom, of course, is going to be a u. But now, see, I still got this x squared sitting up here. Well, what's x squared? It is u minus 1. Well, I wouldn't even square root it, right? Because we got that x squared sitting there. See, so I took the x cubed and I split it into an x and an x squared. So the x dx is replaced with 1/2 du. The bottom is u. And then I got that extra x squared sitting there. Well, x squared is u minus 1. So now I have that, which we can split apart. So now we got 1 minus 1 over u. So that would be 1/2. Oh, wait. I'm going too far, aren't I? Yeah, I keep forgetting it's multiple choice. We got to look at this. See, so I'm looking at those two right there, right? Because the 2's on the bottom. So both of these match up, but then what you got to realize is I can't use 0, 2 because those are x values. So that eliminates that one. I've got to put 0 in here for x and I get a 1. And I put a 2 in here for x and I get a 5. And that is the choice thing. Yeah, I was going too far. And that's a good lesson. I mean, when you're on a multiple choice, look at your answers. See what they look like. That gives you a hint as to what you're going to be, kind of trying to get. Trying to make it look good. All right. Any others? Okay, we'll do some more work on this later in the week, but we are going to try to wrap up chapter 6 this week, get a quiz in so we can kind of start fresh after break, and get the Niobrara thing done, hand it in on Thursday, and so forth. So, all right, let's go ahead and get started then with what we have to cover today, and get to our homework as we need to. So, all right, so what we're going to do is head into section 6.2 now. Okay, 6.2, and this is going to be about maximum error, error bounds. We start talking about in section 1 a little bit, but today we're gonna actually get formulas that we get to use, and so we're gonna get into the theory here a little bit for a while. All right, I think it's worth jotting down. I think it's good to go through, but in the end, when it's all said and done, we're going to come up with a formula that we can just kind of plug into, which is nice. So you will need your calculators here at some point. So the first thing we want to do is investigate left and right rectangles. So I've drawn a little bit of a picture here. I've just got a random function, and I've got one subinterval, and I'm going to let it be h. We're going to use h here for a second. H units wide is my subinterval. And I've drawn in black, I've got a left rectangle, and in blue, I've got a right rectangle. And so we can see how much error there is. Okay, so here's what we want to talk about today. We want to talk about maximum error. What is the worst case scenario? Well, let's go on the other side of that. What's the best case scenario? What function would make a left or a right perfect? No error. What kind of line? Horizontal line. If you have a horizontal line, zero slope, a left and a right rectangle are going to fit perfect, no error. Okay, but everything else is going to have error. What's going to make the error worse? Well, okay, the worst would be vertical line, which is not a function, but I mean, what's going to make it get worse if the increasing slope? And we talked about this the other day. The bigger the slope that the function has, the more error there's going to be. If we want to find the maximum error, we want the worst case scenario. All right, so we need to measure the slope. Well, what do we have that measures the slope? The derivative, the first derivative. The first derivative of a function tells us the slope. So here's what we're going to do. We're going to, in this interval right here, we're going to find the maximum slope of that function. And we're going to call this K1. K1 is going to be the max slope of f of x. Now, let's think about this now. What if, we got to think about the word max. What if the graph goes up and down? So it's got some positive and some negative slope. What's worse? What's worse for error? If it goes up steeply or down steeply? It doesn't matter, right? It doesn't matter if the graph goes up steeply or down steeply. A left and a right rectangle is going to have a lot of error, right? So we don't really care if it's positive slope or negative. So when I say a max slope, if the biggest positive slope it has is 2 and the biggest negative slope it has is -3, which is worse? -3. So here's what we're going to talk about when we talk about max slope. We're going to talk about the max, and the slope, of course, we just said is a derivative, f prime, right? So the max slope would be the max of this graph, and we don't care if it's positive or negative, so we're going to put bars in it, right? So if you took f prime and found its max value, and you didn't care if it was positive or negative, let's make them all positive, so let's put bars around it. Okay, that would be our worst case scenario, right? We're going to call that K1. So maybe it's 3, right? So maybe the worst slope, the steepest this graph ever is 3. Okay? And here's what we're going to do. To make the worst case scenario, we're going to pretend that it's that slope the whole time. Does that make sense?
Yeah.
Let's find the max slope, and then let's pretend it has that slope the whole time. So, what that would give us would be a picture something like this. So I've got a function. Here's a left. We'll just use a left. Right's going to be the same thing. So here's a left rectangle. The gray is the amount of air. But we're going to pretend, we're going to find the max steepness this graph has, and we're going to pretend, starting back here at the left edge, that it does that the whole time. So we're going to pretend that F is actually here. So this, in here, would actually be our air, right? Now we know that there isn't probably that much. You see what I'm doing here now? It's in abstract here a little bit, so we got to think of it. But what we're saying is, let's find the biggest the derivative ever is. That'll be the biggest the slope ever is. Let's pretend that the graph has that slope the whole time. So let's pretend the graph goes here and not here. Let's find this amount of error, and let's pretend that's how much error there is, even though we know there's probably less. You know what I'm saying? So that will give us the worst case scenario for how much error we have, and that's what we're looking for, if we're looking for max error. So what we need is the area of this. Now, for a linear, this works out pretty nice. Since we're going to say it has a constant slope, that max slope, we're going to say it's that the whole time. It gives us a linear, which gives us a triangle, which we can just do easily. Okay, so what is that area? Okay, so that's our job right now, is to find the area of that triangle. Well, that's 1/2 the base times the height. Okay, well, now remember, this is just one subinterval. So what's the base? Well, the base would be delta x, our width. Well, what's delta x? That's b minus a over n, right? So the base of this triangle is one width, which is b minus a over n. What's this height? Now this is a little harder. Oh, but remember, our slope is k1. Now k1 is rise over, slope is rise over run, right? Right? Are you with me? K1 is this slope. And the slope is rise over run. So it's this over this. Okay, let's just call this h for height right now. It's a different h than what I had in my other pictures. Let's just call this h for height on the triangle. Now what do we just call this right here? Delta x, right? So my k1 is just equal to h rise over the run delta x, right? So now let's multiply the delta x over there. So delta x times k1 is our h. So our height of our triangle is delta x times k1. And what did we say delta x was? That was b minus a. So we got another one. So let's just square it. And then times k1. Correct? So this triangle is that right there. So let's rewrite that a little bit. I'm going to put that over 1. So the top would have k1. It would have b minus a squared. The bottom will have 2 n squared, correct? Okay, that right there. Now let's think about what we just got there. Now, that is this blue area. That is the most my left rectangle could be off, right? Here's our function. The gray is how much it's actually off. But remember, the idea is that we don't know exactly what this area is. So what we're trying to find out is how far off is the left rectangle. So the gray is how much it's off, but we're going to, since we can't find that gray, we don't know what that is because we don't know what the actual area is. We're going to say, what's the worst? What's the biggest that the gray could be? Well, the biggest would be find the steepest the blue graph is, pretend that that graph is that the whole time, and then find that area. And at least we know the gray can't be any bigger than this. Okay, this is the most that the gray can be. And again, what was K1? The max of F prime, right? The max of F prime, the steepest slope. Okay, and B minus A is our interval. Now, okay, But there's one additional thing we have to do. This was on one subinterval. This was on one subinterval. We're going to have n subintervals, so we got to times that by n. So the max error for the whole region from A to B, I've got to times that by n. So we times that by n, that's going to cancel one of those n's, and we get that right there. And that is our first formula. I think they call this in your book, I think they talk about it, I think in your book this is called theorem 2. I don't care about the name of the theorem, no, theorem 3. Somebody in the homework will say, use theorem 3, and this is the formula they're talking about. So here it is right here. So K1 times B minus A quantity squared over 2n, and it's the same for rights. It's exactly the same for rights. All right. Now, would we have all that information? Well, yeah, because, well, let's just do an example. Let's do a problem. Okay, right here. What's that? No, we did already. We times by n right here.
Oh, okay. Yeah.
Remember, and that's how we canceled that n squared down there on the bottom. Okay, and so it's just n down there on the bottom. All right, so here's our problem. So let's do an example. Let's just do an example and see how we would use this. All right, so here's our integral. Sine x squared, and get your calculators out now. Sine x squared from 0 to 1. You can't do an antiderivative. You can't do geometry on this because it's some weird function. We have to do an approximation. So we're going to do a left approximation with 10 rectangles. We're going to do an L10, which means you automatically get to go to that area document. Right? We automatically get to use that area document. So just for right now, just do L, or just tell me what you're getting for L10. And I think it actually tells you the exact integral too. How much you getting?
Point for left, you said?
Yeah,
0.26909.
0.26909. What's after the 9? So 10 maybe. I mean, yeah, it's that'd be 3 decimals, but I like 5. So, all right. So that's what we think. Now, what did it say the exact area is actually? Okay. I'm gonna, for the most part, pretend we don't even know that's what it is. But I mean, we'll refer to it whatever. But the idea is, okay. The idea here is, okay, we've just done 10 left rectangles. What we'd like to know is how far off are we? And remember how I said your calculator, when your calculator gets this 0.31026, how does it know that it's accurate out to so many decimal places? Well, here's how it knows. Because it knows the most it can be off. Now, it doesn't know how many, the calculator doesn't know how many decimals it's accurate to, but it knows it's at least accurate to a certain number. That's the key. It might be accurate past that, but at least it knows for sure it's accurate out to a certain number, which I think is like 12 on your calculator. I think it gives you accurate to 10 or 12 or something like that. How does it know? So this is what we're working on. So L10, all right, is 0.26910. So we're looking for that. All right, well, here's our little formula. So the error, so I minus L10, according to the formula, is less than or equal to K1, okay, here's the formula. Okay, here's the formula. All right, but now, For K1, I'm just going to put a box for a minute. All right? We'll deal with that in a second. Okay, what do I put in for B minus A? 1 minus, because what's A and B? This right here, right? This right here is A and B. All right? And then squared. And then what do I put in for the N on the bottom? I put in 10. See, so we'll have all that information. See, N is 10, and 2 is just part of the formula. What we need now is the K1. And so when I'm grading this on our next quiz, and you're using these theorems, I'm going to be looking for what number you put in the box. And different people will come up with different numbers. You'll have a range of what's acceptable. Okay, we got to talk about that. So what is K1 again? Max slope of F, which would be the max of F prime, right? F prime is the slopes. So we want the slope of F or the max of F prime. So here's how I would suggest doing this, and here's how I'm going to let you do this, is get on your calculators. And let's graph F prime. Now, if you want to let the calculator do F prime for you, I don't care. So first thing we need is the derivative of F. So for this problem, it would be what? 2x. So F prime is going to be 2x times cosine of x squared. Right? The derivative of sine is cosine. Leave the inside alone. Kick out the derivative inside. But you can let the calculator do that for you. I'm fine with that. So there's F prime. Now, you've got two options at this point. I think graphing it is the best way to go. My calculator is really slow at this point. So now, make sure you put a time sign in between there, guys. This is going to be a big deal because you're going to get into these, and on the quiz, I don't want you to mess up with that. So it's 2x times cosine of x squared. You can't put that x next to that c. It'll foul you up. Now, what would be a good, that's a mess. What could we do here now? Window to 0 to 1. Zoom fit would be a great thing to be using here. I would definitely do that. That didn't work very well. Thought I did zoom fit. All right, is that what you're getting? Okay. Now, the nice thing about that is it's all positive. But what if we'd have got some positive and some negative? Trace, and so if I had a positive here that was 2.7 something, and I had a negative here that was 3.8 something negative, I'd go with the 3.8, right? Or you could just do the absolute value of F prime. When I went and graphed this, I could have, now you can't put bars around, I think you have to type ABS. I think you have to type ABS and then the function when you graph it. Okay, you can't, there's that vertical bar, but that doesn't work for absolute value. I think maybe in the template here there is an absolute value somewhere. No, where is it? Over here? Right here. Yeah, there is absolute value bars where you get the integral and stuff, so you could do the bars there. So if you want to avoid that positive negative issue, just graph the absolute value. But okay, so what did we do? We figured we found F prime, and then we graphed F prime. And then we're looking for the max of it. Okay, so anyway, when we trace, and the nice thing about it, I think, when you trace, doesn't it tell you the maximum? Now, there's something important to think about here, though. So if I go, so you're telling me it'll go right to the maximum? Oh, whoops. You also can analyze graph and go to the maximum, find your lower and upper bound. That'll work too. Now, one thing we got to be careful. Are you guys getting the same decimal places I'm getting? Are you getting 5?
I just have 1.28.
Okay. Now, at this point, I think it's probably important for us to go into our settings. Let's see, probably in the document.
Display digits.
Settings, display digits. What's yours say? Yours say float 3?
Is this for documents or for graphs?
Well, I think it's,
Mine says float. Mine just says float.
and you're only getting 1.28?
But if you go,
Okay.
If you go to settings, you can
Oh, under menu. That's where we want. In the scratch pad, go to menu, not dock. Go to menu, and then settings, and then does it say float 3 there? Change that to float, and that's the scratch pad. That's right, because the other one is just for documents, right? So in menu, change that to float, and then you should get more. And it's kind of, and then hit make default, and then hit OK. Now, because here's what's important about this. And here's where you get a little bit of leeway. So the number we're looking at is the 1.28367. Now remember what this graph is. This is f prime. So these y values are what? The slopes of the f graph. We're looking for that K1 value. We're looking for what number to put in here. We want the max slope. Now we know, we can tell by looking at this graph, that most of the time the slopes are less than 1.28. But what we're going to do is pretend that they're going to have this slope the whole time, which will give us the most error. Since we want K1 to be the worst case scenario, what number would be an acceptable number to use for K1? 1.3. Would 1.3 be an acceptable number to use? Well, I know. That's why I'm asking this, because I got to make sure we understand this. Okay, K1 is supposed to be the max slope of F. The most it could ever be. Okay? Just like, go ahead, say that again. That's right. You have to round, would one, so back to my question, would 1.3 be okay? Yes. Would 1.29 be okay? Would 1.28 be okay? No. Now, I know this is getting really picky, okay? But it wouldn't be accurate to say that the biggest the slope ever is for this graph, the F graph, is 1.28. Because it gets a little bigger now, 1.283, right? So what Jake said is exactly right. We've always got to round up. No matter what digit we go to, we've got to round up. Okay? Now, to me, would it be accurate to say, accurate's a bad word, would it be correct for me to say that K1 could be 2?
Wouldn't be accurate, but it could be correct.
That would be correct. K1 is the max of F prime. It'll never get above that, right? The slope will never be above 2 for this graph. Okay? But that's like me saying that 5 million is the max of how much money I have in my pocket. It's correct, but it's not very useful. It doesn't tell you much about how much money I have. So the closer we can be to the max and still have it be the max is what we want. So 1.3 would be okay. 1.29 would be better. 1.284 would be even better. And at that point, I think that's fine, right? Now, it depends on how big this number is. If this number was 30.283, do we really need to go to 30.284? You know, 30.3 would probably be fine, right? But if it's this small of a number, I don't like 1.3. I think I would go 1.29 or 1.284. You know what I'm saying? I'm going to cut you some slack on that. But we want it to be just barely above whatever this number is. That's what we want to do. We want to pick a number that's just barely above whatever this is. So if this was 300.283, then 301. right, would be okay. Rounding it all the way up to a whole number would be fine. But here, rounding up to 2 would be bad because you're almost doubling it. And so that would not be a good idea. You see what I'm saying? So we want to pick something that's just barely above whatever that number is. So once you get the hang of that, it's really easy to do. So you graph f prime, absolute value would be good, do your zoom fit, find that maximum, take that number, just barely round it up because what we're doing is the worst case scenario. All right, once we have that number, 1.284, we stick that right there. That's our K1. Now remember from that picture we did earlier, what we have just done there is assume that our graph is going to have our F graph, this graph, the F graph, because remember we graphed F prime earlier. The F graph, we're going to assume it has that slope the whole time. So we're finding that blue rectangle of area that we had before when we do this. And so that's definitely going to be the most error we could possibly have. So go ahead and calculate that out. So it's going to be 1.284 times 1, which is easy, divided by 20. How much? So 0.0642. So what I'll be looking for in a quiz when I do this, and when we check our homework tomorrow, I'll be looking for this number right here. What number did you use for K1? The number in the box. I'll be looking at that number, and then of course this number should be, will be based on whatever you use there. Now, if somebody on the quiz used 1.29, good enough. 1.3, it depends if I like you. Right. But so we got that. Now, what did we find? What did we find? We have said that this approximation. Well, you tell me, what have we just said with this number? That's the most this can be off. So if we add that or subtract it, because we don't know if this is over or under, right? The most this could be off would be this. So we could get a bound. So the final thing might be, if all they want is a max error, I would stop with this number right here. If they want an actual error bound, then we would add and subtract this number onto our L10. So go ahead and do that for me. Let's add onto there and let's subtract that from there.
No, wait, you put I there?
I is the exact answer. So what this is saying is that we know I is going to, because we know what L10 is, right? We wouldn't put L10 here. L10 is not between here and here. We know what L10 is. What we don't know is what I is. Pretend this isn't here, right? We don't know the exact error. So we did an L10 approximation, and now our question is, how close is that? How close is that?
Wait, why?
Because we cheated and we used our program to tell us what I was. See, right? Because what we're trying to do here is, how does a calculator know when it? Because when the calculator, when you go in on your home screen and you do this and you just type this in and it gives you that 0.3 whatever. How's it getting it? It's doing an approximation method. How does it know that it's accurate, what it's giving you? That's what we're finding out right now. So we went ahead and cheated and let our calculators do L10 for us. We could have done it by hand, right? So we're doing 10 left rectangles. Now, how close is that? Okay, we don't know what this is, right? Because we can't get it exactly, right? All we can do is an approximation. So we just did. We did 10 left rectangles. And we know the most it could be off is this right here. Okay? So, what do you get right here? 0.33, really?
Yep.
Okay, and over here? 0.49. Okay, so this is right in the middle of that, right? This is smack dab in the middle of that, which I think that's what you're thinking. Why don't we write L10 here? It's smack dab in the middle of this, I understand it. But also we know that I is in between here too, right? We know I is in there somewhere because that's the most that our L10 can be off. So we know the exact, now that's not that great.
Yeah, I was just saying.
Yeah.
Putting L10 makes sense.
Well, yeah, if you put L10 in there, yeah, L10 is in between here. But yeah, matter of fact, it's right in between there, right? Because we added .0s. But we also know I is in between there. We know the exact answer's in there. We just don't know where, but we know the exact answer's in there. Now, and again, that's not that useful. That's a pretty big gap from 0.2 to 0.3. Yeah, it's a fairly big gap, but we know it's in there. Okay, we know it's in there. Now, what would have been better? More rectangles, right? If we'd have done an L100, we'd have had a more useful, right? So what would have changed on here? What would have changed on here if we would have done an L100?
We take 2 times 400.
The only thing that would have changed was this number right down here. K1 wouldn't have changed. Our function didn't change, right? B minus A doesn't change. The only thing that changes is that. So let's do that. Let me do that in red. So in your area, go to your area document. Do L100 for me. We'd expect this to be a better approximation. This is where that RSL might be nice to use if you remember it. But then you got to have your function typed into F1. The sine of x squared would have to be in F1. And right now you've got your derivative in F1, so that's kind of confusing. So just using that RAM formula is probably the way to go. What do you get?
306.
0.7. Okay. So now what we've done is we've said, hey, 10 rectangles probably isn't that great. So let's do 100 left rectangles. And now our question is, how close is that? Now again, we're not going to get an exact answer of how close that is, right? Because this is still a function we can't do an antiderivative on, and we can't do geometry, so we don't know exactly what it is. We know as we do more of these, we're going to get closer. But the question is, how close do we at least know we are? Well, that's where this formula comes in. So now instead of a 10 down here, we would have a 100. So what's this number going to be now? Well, won't it just have another 0 in there? Won't you'll divide by 200 instead of 20? I mean, go ahead and do it, but won't it just be 00642? Right? And now let's take that number and add it. Right? Isn't that what you get? Do you see how it's going to get better the more ends you have? Since ends on the bottom, you're going to divide by bigger number. The more subdivision you have, so your max error is going to get smaller and smaller and smaller. Now let's take that number and let's add it and subtract it from that. And what do we get? 0.31249, and now isn't that getting better? We're really narrowing down the gap, right? And if we keep going, we're going to start seeing that, hey, my first decimal place is the same. My second decimal place is the same. So we know we're accurate out to a couple decimal places because we know it's got to be in between there. That's what, and it's probably, this is not how much it's off. This is the most it could be off, right? That's an important distinction to make. All right? Now, let's ask ourselves this, and this is the question the calculator is asking then. Okay? So now let's do this question. Oh, whoops. That's not a 10. Yeah, oh, yeah, you want to be careful about that. Yeah. Okay, now what if we wanted to know, how many left rectangles, and this is the question the calculator asked, how many ends, how many subdivisions, how many left rectangles will it take to get 4 decimal place accuracy? Well, 4 decimal place accuracy would be this. Remember when we did Newton's method and we said however many zeros you have in here is how many decimal place accuracy you have? Because think about it. This is our max error. What I'm doing is telling you what my max error needs to be. If I have 4 zeros here, when I add or subtract, those decimal places won't change, right? Let's change that from a 5 to a 1. Let's change that from a 5 to 1 because then it could probably change. So let's go here. Okay? So 4 zeros here, this would be like saying I'm going to get 4 decimal place accuracy. So I want my max error to be this. So what I do is I take my formula. So my K1 was 1.24. Remember, that's not going to change here, right? When I change n, or I change my max error over here, that doesn't change. That for this function, for 0 to 1, sine of x squared, right? As long as I don't change the interval or the function, that k1 is still going to be the same. So what was it? 1.284. That was the k1, and then 1 minus 0 squared, and then what would be on the bottom? 2n. We don't know it. That's what we're trying to find, right? How many rectangles will it take to have this as my max error? Right? So what we do is we solve that equation. We just solve that equation. Now, it's a pretty easy equation to solve. You could type in your calculator and actually let it solve it, and you can use equals if you want. But, so the top, now this is a pretty easy one because that's going to be 1. So this would be 1.284 less than or equal to, and if I multiply the 2n over to here, this would be 0.00002n, right? So now I divide by 0.0002, right? So what's 1.284 divided by 0.00002? No, it should be a big number. 6,000. 64,000 n is greater than or equal to 64,200. If I did 64,200 left rectangles, I would be guaranteed to be within 4 decimal places. Now, remember, that's a worst case scenario. This number, this formula assumed that the graph had that slope the whole time. We know it doesn't. So you probably will get 5, 6, 7 decimal places of accuracy if you did this many left rectangles. Don't do that on the program. It'll take a while. Well, you can. I don't care. I mean, go ahead. So if you did that many left rectangles, you would probably get 5, 6, 7, 8 decimal places. But that's how your calculator knows. It runs this little, now it's not with lefts because it wouldn't need near this many. But it's got a routine in here based on this same kind of theory that it will say, okay, for this function in this interval, I need to do this many subdivisions to give me my 12 decimal places of accuracy. It runs that calculation, and then it says, okay, now let's do the approximation with that many, and then it spits it out all in
It's too good.
part seconds. But that, because we're using the worst case scenario. Okay, so it's guaranteed, we know it's guaranteed to be accurate to 4 decimal places right there. So these are the 2 types of problems I would have you do. One would be find the error bound, find the max error. So then you would have a number of n. So what's the max error that 10 lefts would do? So you know what n is, you just plug into this formula. And how many n's, how many subdivisions would you need to get within a certain amount? Okay, be able to do those 2 things. And both of them are based on finding this k1 value. Okay, find that k1 value. All right. Now, the next thing, and we'll hurry through this one a little bit differently, or go through this a little bit differently. But now what about, and it's the same for rights. So left to right, same formula. Left to right, same formula. Okay? So then the question becomes, what about trapezoids and midpoints? What about trapezoids and midpoints? Now, I'm going to do this, I'm going to work through this one a little bit differently. We'll do trapezoid first. So, because we won't be able to do this same picture. We won't be able to do this same picture because it doesn't have to do with slope. What makes a midpoint in a trapezoid be off? Concave up and down. Concave up and down. And what did we say the other day? What's the measure of concavity? Second derivative, not the first derivative. So it's not just slope. So we're not going to get a nice geometry thing to do. So we're going to have to do something a little different. So here's what we're going to do. We're going to pretend that our function f is, back up. We're going to pretend, we're going to call it k2 for second derivative. We're going to pretend that our second derivative is this number, k2, all the time. The worst case concavity. We're going to let k2 be the max, so it's going to work exactly the same way. k2 is going to be the max of f double prime with bars around it. We don't care if it's concave up or concave down, okay? So we don't care if it's positive or negative. So we put bars around it. So K2 is going to work the same way. We'll graph this, when we do it, we'll graph the second derivative with bars around it. We'll do a zoom fit, we'll trace to the max, and we'll round up just a teeny bit. Okay, so it's the same thing except using second derivative. Okay, but what's our formula? Well, if we're going to assume our f double prime is K2 the whole time, then let's do an antiderivative to find f prime. That would be K2 times x. Everybody with me? Now, normally, when I do an antiderivative, I would do what? Tack on a plus c. We're not going to worry about the plus c right now. Okay? So, you see what I just did there? We're going to assume the second derivative is K2 the whole time. So that's just a number. K2 is just a number. So I do the antiderivative, be that number times x. And then I'm going to do the antiderivative again. And so that'd be what? That'd raise up to a 2 and divide by 2. So it'd be 1/2 K2 x squared. There would be a function whose second derivative would be K2. Right? With me? So what we're going to do is pretend this is our function. We're going to pretend this is our function, and it's that, because this function has that concavity the whole time. Our worst case scenario. All right, now, I'm going to do this. Here's my function, here's my f. Okay, I'm going to go one subinterval from 0 to h, and I'm going to find that area right there. Okay, so I'm going to do that integral. So I'm going to go from 0 to h, and I'm going to do 1/2 K2 x squared dx. Okay, I'm just going to do that area. Okay, now remember, this is my worst case scenario area. This is my worst case scenario area right here. Worst case function with the most concavity you can have is this function, and I'm going to do that area under it. Now I'm going to do one subinterval. I'm just going to go from 0 to 8. So do the antiderivative of that real quick. Okay. No. Not, we're dealing with this function right here. Do the antiderivative of this function right here. Okay, remember K2 is just a number, so what we're doing is developing the formula here, guys. We're developing the formula. So we'd raise that up to a 3, divide by 3, so that'd be 1/6 K2 x cubed from 0 to h, right? So we plug in our h, so we get 1/6 K2 h cubed minus 0, right? And then what did we say h was? H is one width. What? Right? H is one width. So that's b minus a over n, right? So this would be 1/6 K2, and then it would be b minus a over n cubed. H is this distance right here, which is just a width, delta x. And so I'm substituting the h for b minus a over 1 width. So now, I can put the K2 over 1. So on top, I'm going to have b minus a cubed. Oh, and a K2 in front of it. And on the bottom, I'll have a 6 and an n cubed, right? So I got a K2 on top and a b minus a cubed on top. And on the bottom, I got a 6 and an n cubed. Now, that's the area of one width. Okay, well, hang on. Let's stay with one width. But that's not the error. It's the area. This is my worst case function. So this is my amount of area under that. Now, what would be, let's do a midpoint. That would be easier. Let's do a midpoint. That would be easier. So what would be a midpoint for this one width? What would be one midpoint rectangle? It'd be halfway plugged into that function, right? So what's halfway? H over 2 plugged into this function, right? So one midpoint rectangle would be h over 2 plugged into this function. So it'd be 1/2 K2. Good job of staying with me after a 3-day weekend. That's awesome. Not easy to do here. Oh, come on, hang in there, we're getting there. Remember, what I'm doing here now is, I just got this area under the function. Now what I'm doing is one midpoint rectangle area. And so I need the height and the width, right? I need the height and the width. So the height would be the midpoint plugged into that function. So that's that right there. And then times the width. What's the width of the rectangle? H. So I got to take that times H. Now let's work that out. So let's see, that would be an H squared. All on top of what I have. I'd have a K2. I'd have a H cubed all over, not 4, 8, because 2 squared down here is 4, and then that 2 would be 8. And then times, no, oh, wait, time out, yeah, not times n yet, we haven't got the ands in there yet. So this would be one midpoint rectangle, right? The height times the width, right? So that'd be one midpoint rectangle. So what's my error now? What's my error? This is the area under the function, the worst case function. And this is the rectangle.
So those minus.
So subtract those two would be the error, the max error, the worst case error, right? So we subtract those two. Oh, I should put my h in here. Now I can put my b minus a over n in here, right? For my h. So I'd have b minus a over n in here for my h. So that'd be a b minus, so this would be a k2. Before we subtract them, let's write them the same. So this would be a b minus a cubed over a what? 8n cubed. So now what I need to do, let's change colors here a little bit. That's too much black. So let's subtract these. So this would be a k2 b minus a cubed over 6n cubed. And then I'd want to subtract over 8. That's going to be pretty easy to subtract, really. Well, because I just need a common denominator. So what does 6 and 8 both go into? Yeah, littler than that. 24. So couldn't I take this one times 4, top and bottom? Take this one times 3, top and bottom?
We have calculators,
We're there. We're done. We're basically done. So what do we got? We got 4 of this thing minus 3 of that thing. So we end up with just 1 of that thing, right? So we end up with just k2 b minus a cubed. That's nice. Over what? 24n cubed. Our common denominator, right? Our common denominator of the two is a 24n cubed. Now we take it times n. That's right. This is, okay, so again, this here was the area under the max concavity. This was the area under one midpoint rectangle. We subtract those. That's the max error that the midpoint could have for that one subdivision. But we have n subdivisions, so we need to multiply that by n. And then that would change to a 2 down there. And voila, if we look on page, or whatever a magician would say, an abracadabra or something at the end. And then, so what we would come up with would be this formula, which is in your book for midpoint. And you will not have to recreate that. But I appreciate you going along with me for the ride. That's a squared. No, it's not. We won't do the other one. I'll spare you that. But it would be very.
I thought we were doing trapezoids.
We were.
We just switched
I
the
did
midpoints,
switch
and I was like, whoa.
All of a sudden, well, here's why. I know. Well, that was bad. I did. Tried to sneak it in. I tried to switch midstream and not.
Darker.
But,
I just went straight to the.
but I did it for you. I did it for you. Well, right here, the trapezoid would have got messy. Trapezoid would have been harder here than
I
midpoint.
can see it. It was plenty messy.
It was plenty messy there, and I thought, yeah, let's do midpoint. So the only thing that changes is this ends up being a 12 instead of a 24, which,
That actually seems clear.
well, when it got done, it would have been cleaner, but getting there wouldn't have been quite as clean. And which actually shows, remember, the bigger, in this red part, remember, this is the max error, right? In the formula, this is max error. So the smaller this is, the better, right? And what makes this smaller is bigger numbers in the bottom.
So
So,
midpoints are twice as
Midpoints are twice as accurate, which we've talked about, right? We've talked about how the midpoints are twice as accurate, and sure enough, in the formula, that shows up as well. So now, understand when you see when you're doing midpoint and trapezoid, remember they're based on concavity, the error is, so therefore second derivatives involved. K2 is the max of F double prime. So the only thing that changes when you do this problem that we did here, the only thing that would change now for an M10 kind of calculation is we would have, this would be cubed, this would be 24n squared, and this would be K2. So finding this number, you would find the second derivative of this, which would need a product rule, but I'm letting you use your calculator, so this is where it would really pay off to use a calculator. So you can use a calculator to find your second derivative, graph the second derivative from 0 to 1, do a zoom fit, find the max, bump it up just a little tiny bit, right? Always round up. That goes there. Work this out, and then all the rest of that is the same. But these numbers will be much smaller. Your max error will be much smaller because look at the formula. The formula, whatever, think about it now, what makes the error smaller is when the bottom is bigger. Well, look what's on the bottom, n squared. So if you have 10 subdivisions, you're going to be dividing by 100. If you have 100 subdivisions, you're going to be dividing by 10,000, right? So the bottom's going to get big much faster with trapezoids and midpoints. They're so much more accurate. The max error is going to be better. So we need to be able to use those formulas. I don't think even, I'm trying to think on the quiz, I'm probably going to give them to you. You don't have to memorize them probably. I'll give you those. You're going to have to know what K1 means. You're going to have to know what K2 means. And you have to be able to find those. But that's pretty much it. So what your homework is just like this problem we did together. Here's your homework.
Yeah, like let your brain rest.
That was this weekend. Now we got to work. This weekend. Just these two basic things, okay? As far as working problems. Now there might be some questions they ask you, the theory parts of it a little bit, to understand it. But be able to find that K1, graph it, find the K1, be able to work out this max error, do the error bound, or be able to find out how many ends it takes, to be accurate within a certain amount. Okay, so on your homework sheet at 6.2, the 6.2 line, third line down, and whenever it says use the theorem 3 error bounds, those are the formulas. Okay.
So whenever I feel like I can use my calculator on, I can.
You can, the calculator is our friend on this stuff. Absolutely. We're graphing the first and second derivatives. We're using them to find the first and second derivatives. We're rounding up. We're using them to do these calculations for us in the formulas. Absolutely. Okay? Yes?
Is there like this same thing but with the Simpsons so they get even closer? Like
There is. Yeah, that's a great question. We're not going to do it.
But there's the same thing.
There's a formula, and it actually uses the fourth derivative in it.
Really?
Well, because here's why. Remember we said a perfect fit is a horizontal line? So anything off of horizontal, which means if it has slope, is going to be off. Well, that's why first derivative is involved. We said that trapezoid and midpoints are based on concavity, because trapezoids and midpoints will fit a line, any line, perfectly. But as soon as it curves, then you're going to have a problem. And so that's why the second derivative measures that, and that's why that's involved. But it turns out Simpson's rule fits quadratics perfectly. So it will take a cubic to be off, but actually it turns out even better than that. Simpson's actually fits cubics perfectly also.
Wow.
So it takes more and so
What does the
well, here's what the third derivative measures the rate of change of the second derivative. So it finds the rate of change of the concavity. But Simpson's rule fits those perfectly, so you need the rate of change of the third derivative, which is the fourth derivative. See, because a cubic, if you do three derivatives, will be a constant. And the fourth derivative won't be, there'll be a change. And so that's why it takes a fourth derivative, because that's the rate of change of the third derivative. So you need the max of the fourth derivative to do the max error on Simpson's.
He could just be totally.
And,
Totally.
no, it's in
I
your
know,
book.
yeah.
It's in your book. It's
I
on.
mean, it makes sense what he's saying, but. I mean, you could be making all this.
It's on page 405. It's on page 405, and not only that, in that error formula, it's into the fourth down here. That's why Simpson is so accurate. Because if you do 10 subdivisions, you do just 10 subdivision on Simpson, you're dividing by 10,000. So yeah, the formula's on page 405. So
Okay.
it uses K4, which is the fourth derivative. Yeah. Yeah. Oh yeah. Are you late, or was that perfect timing?
No, that's perfect.
Oh, okay. I thought maybe you were loving it so much you stayed extra. You stayed
it was
over.
Perfect. I don't know. I might have had to stay if we were
Right. If we.
Like,
No,
no,
he
he
would
would
not.
not say to you back.
Like, wait. He's just walking around.
Nice. You have another assignment sheet?
Yeah.
Are we ever doing that sort of thing? Or are we just gonna?
I don't want to.
It exists since. Yeah, we're not gonna do
The Simpsons formula, error bound.
It's like it exists and you can look it up.
It's there. Yeah.
Oh, yeah, I forgot
Oh God. Yeah. No. The next quiz will definitely be calculated.
Surprise, no copy.
No, you'll get a user. But you will, again, you will have to show your setup. You'll have to show your setup, and I'll be looking at this number in the box here, that K1 value, K2 value, to make sure that's correct. Is this somebody's Chromebook? Okay. All right. I didn't know. My bear can't tell you. Okay.